This is section 4.2, part B, how to experiment badly and well. Experiments are the preferred method for examining the effects of one variable on another. By imposing the specific treatment of interest and controlling other influences, we can pin down cause and effect. Good designs are essential for effective experiments, just as they are for sampling. A high school regularly offers a review course to prepare students for the SAT. This year, budget cuts will allow the school to offer only an online version of the course. Over the past 10 years, average SAT scores of students in the classroom course was 1620. The online group gets an average score of 1780. That's roughly 10% higher than the long-term average for those who took the classroom review course. Is the online course more effective? This experiment has a very simple design. A group of students, who are the subjects, were exposed to a treatment, the online course, and the outcome was their SAT scores was observed. Here is the design. So we have students take the online course, and then we receive their SAT scores. A closer look shows that the students in the online course were quite different from the students who take the classroom course in the past years. They had higher GPAs and were taking more AP classes. The effects of the online versus in-class instruction is mixed with the effects of those lurking variables. Maybe the online students earned higher SAT scores because they were smarter to begin with, not because the online course prepared them better. This confounding prevents us from concluding that the online course is more effective than the classroom instruction. So many laboratory experiments use a design like the one for that online SAT course exam. We have experimental units, we know their treatment, and then we measure the response. In a lab environment, simple designs often work well. Field experiments and experiments with animals and people deal with more variable conditions. The remedy for the confounding in the SAT prep course example is to do a comparative experiment in which some students are taught in the classroom and the other similar students take the course online. Most well-designed experiments compare two or more treatments. Comparison alone isn't enough to produce results we can trust. If the treatments are given to groups that differ greatly when the experiment begins, bias will result. The solution to the problem of bias is random selection. In experiments, the solution is random assignment. So in an experiment, we have random assignment, which means that experimental units are assigned to their treatments at random, that is using some kind of chance process. This year, the high school has enough budget money to compare the online SAT course with the traditional classroom instruction. 50 students have agreed to participate in an experiment comparing the two instructional methods. Describe how you would randomly assign 25 students to each of the two methods. And this first one, you need to use 50 identical slips of paper. So what you could do is write each student's name on a slip of paper. The first 25 names that are pulled out will take the in-class course, and the next 25 names that are pulled out would take the online course. Next, we need to describe how we would divide the students using table D. So first, you would have to assign each student a number between 0, 1, and 50. You would then randomly select a line on table D, and you would divide that line into 2-digit increments. If the number is between 0, 1, and 50, then that would be a student that is selected. If it is not one of those numbers, you would skip it, or if it is a duplicate, you would skip it until you get 25 students to put in the in-class course. And then the last 25 students, the ones who were not selected, would take the online course. Using technology. So again, you would have to assign each student a number, 1 through 50, but then you could just use a random integer generator on your calculator and randomly generate the first 25 numbers you get would be the students in the in-class course, and the other students would take the online version. The experimental design in this experiment is comparative because it compares two treatments. the two different instructional settings. It is randomized because the subjects are assigned to the treatments by chance. This type of design is called a completely randomized design. In a completely randomized design, the treatments are assigned to all the experimental units completely by chance. So we had the 50 volunteers, and we're randomly going to assign them to groups 1 and groups 2. Then we're going to give them the treatments, and then we'll compare the two different groups. Notice the definition of a completely randomized design does not require that each treatment be assigned to an equal number of experimental units. It does specify that the assignment of the treatments must occur completely at random. So when you go to take your AP exam, if you were asked to describe the design of experiment on the AP exam, you wouldn't get full credit for a diagram like the one we just saw on that previous slide. You are expected to describe how the treatments are assigned to the experimental units and to clearly state what will be measured and compared. Some students prefer to start with a diagram and then add a few sentences at the end. Others choose to skip the diagram, but put their entire response in a narrative form. Many utility companies have introduced programs to encourage energy conservation among their customers. An electric company considered placing small digital displays in the household to show current electricity use and what the cost would be if they used that amount continued throughout the month. Will the displays reduce electricity use? One cheaper approach is to give customers a chart and information about monitoring their electricity use from their outside meter. Would this method work almost as well? The company decides to conduct an experiment to compare these two approaches, display chart, with a control group of customers who are receiving information about energy consumption but have no help monitoring their electricity use. So outline a completely randomized design involving 60 single-family residents in the same city who are willing to participate in such an experiment. Write a few sentences to describe how you would implement your design. So we have 60 different families and we have 3 different treatments. We have a control group who has no information. We have the group that just gets the chart and information. And then we have a group that actually has the indoor monitoring system. So you would randomly assign 20 families to each one of those treatments, apply those treatments to each family, and then compare how much energy they used at the end. The primary purpose of a control group is to provide a baseline for comparing the effects of the other treatments. Without such a comparison group, we wouldn't be able to tell whether homes with digital displays or charts use any less energy than homes without such aids. Many experiments, like the one in the previous example, include a control group that receives an inactive treatment. However, a control group can be given an active treatment. Suppose that we want to compare the effectiveness of a new developed drug for treating a serious disease with a drug that's already known to work. In that case, the experimental units that receives the existing drug would be your control group. Some experimental designs don't include a control group. That's appropriate if researchers simply want to compare the effects of several treatments and not to determine whether any of them work better than an inactive treatment. Music students often don't evaluate their own performances accurately. Can small group discussions help? The subjects were 29 students preparing for their end of semester performance. That is an important part of their grade. Assign 15 students to the treatment, which is they videotape a performance, ask students to evaluate it, and then have students discuss the tape with a small group of other students. The remaining 14 students form a control group who watch and evaluate their tapes alone. At the end of the semester, the discussion group students evaluate their final performance more accurately. Outline a completely randomized design for this experiment. So we have the 29 students, and we're randomly going to assign 15 of them to group 1 and 14 of them to group 2. Now, group 1 will receive the treatment of evaluating their performance in a small group, and group 2 will receive the treatment of just evaluating their performance alone. And then afterwards, we will compare their evaluations. Describe how you would carry out the randomized assignment. Provide enough detail that a classmate could implement your procedures. So using an alphabetized list of the students assigned, each student will be given a number 0, 1 to 29. We would pick a line on the random number table and read off 2-digit numbers until you have 15 numbers that are between 0, 1, and 29. These students belong in the treatment group, where students will meet in small groups. The other students will review their videos alone. What is the purpose of the control group in this experiment? The purpose of the control group is to have a group with which to compare the treatment group. Presumably, the students have been evaluating their own performances by themselves previously. So if you incorporate such a group in your experiment, you can evaluate whether the group work is actually better.